So good morning. Continuing with the chapter 5. So today we will discuss analysis of Rankine cycle. So before the analysis, this assumptions or this calculation will become under per unit mass. Heat transfer per unit mass, work transfer per unit mass, specific we are considering here specific enthalpy. So what we are assuming? We are assuming 1 kg of working substance in the cycle, mass is 1. And so all these are the 4 components, that is your boiler, turbine, condenser and pump. These 4 are the considered as a control volume, or that will be your open system. So here we can apply the steady flow energy equation. So before applying steady flow energy equation, what are the assumptions are taken? The assumptions are here change in kinetic energy and change in potential energy. Change in kinetic energy and change in potential energy are neglected. So tell me, what is your steady flow energy equation? We know that kinetic energy at inlet plus potential energy at inlet plus enthalpy at the inlet plus heat transfer per unit mass is equal to kinetic energy at outlet, kinetic energy at the outlet plus potential energy at the outlet plus enthalpy at outlet, then heat transfer means work must be there. So if you write this steady flow, this is a steady flow energy equation per unit mass. So if you write this all in terms of your change in kinetic energy, then kinetic energy at 2 minus kinetic energy 1, then that is your change in kinetic energy. Change in kinetic energy plus potential energy at outlet minus potential energy at inlet, then change in potential energy plus H2 minus H1, that is enthalpy dH, change in enthalpy, plus W, that is equal to what? Left, that is equal to Q. So we know that here change in kinetic energy is equal to 0, change in potential energy is equal to 0. Okay. So change in kinetic and change in potential energy is equal to 0. Then what is left? The equation reduces to change in enthalpy plus W, that is equal to Q. So Q minus W is equal to what? That is your change in enthalpy. That equation we got. Steady flow energy equation after neglecting the kinetic energy and potential energy, this one. So if we are applying this steady flow energy equation to all the devices, first we are discussing about your pump. Okay. First we are discussing about the pump. So in the pump, at the 3 point is your what? Saturated liquid. The liquid will be saturated liquid will be enter, and what you got? A subcooled liquid. And pump is a work absorbing device. You have to give the work to the pump. So if you apply the steady flow energy equation, so this is in the pump 3 to 4 is a reversible adiabatic compression. So reversible adiabatic means in the pump there will be heat transfer is equal to 0. Heat transfer is equal to 0. So if you apply there, so Q is equal to 0. So what is left? Minus of W. So what is your minus? Minus of W. Minus of W means minus of pump work is a negative, so minus of WP is equal to DH. What is your DH? DH is your change in enthalpy H4 minus S3. So what you got? WP is equal to H4 minus S3. WP is equal to H4 minus S3. And from this calculation, H4 minus S3, we can calculate the WP. So what we can calculate from this calculation? From this calculation, from this equation, we have to calculate is your H4. What is your H4? H4 is equal to WP plus S3. Why we are going to calculate the H4? Because 4 point is your saturated liquid. So if 4 point is your saturated liquid, then 4 point is your subcooled liquid. So if 4 point is your subcooled liquid, to calculate the enthalpy at 4 point, we don't know what is the formula to calculate the enthalpy of 4 point. So but we know how to calculate the enthalpy at 3 point, that is your saturated liquid is your HF, and 3 point is your which pressure? Condenser pressure, that is your PC. So at the by seeing the steam table, condenser pressure, you can calculate the HF, that is equal to S3. So you know that WP is a compression work. For to calculate the WP, that is your V3 into P2 minus V, because WP is equal to what? Compression work is equal, that is your VDP work, change in pressure, or increase, that is V3 is equal to P1 minus P2. So what is V3? V3 3 point is your what? Saturated liquid, that is your VF3. You are calculate VF3 from which pressure? The condenser pressure you can calculate. That is VF3 from the what? Steam table. So you can calculate the S3 and WP, then H4 will be calculated. Okay. Then if you consider a boiler, so what is a boiler? So boiler, 4 point is your inlet to the boiler and 1 point is the outlet from the boiler. This is your inlet and this is your outlet. Okay, so if you are applying the steady flow energy equation, Q minus W is equal to dH. What is your change in enthalpy? H1 minus H4. Change in enthalpy is your H1 minus H4. So here heat addition will be there. Here your Q in will be there, heat addition will be there, but there will be no work transfer. So W is equal to 0. Then what is your heat addition? Q in is equal to what? H1 minus H4. H1 minus H4. That we got from this steady flow energy equation, that Q in is equal to your H1 minus H4. Okay. Then if you go for isentropic expansion in the turbine, so if you consider the turbine Q is equal to 0, then what you got? Minus of Wt is equal to change in enthalpy H2 minus H1, because if you consider the turbine, so here inlet will be at 1 point and outlet will be at 2 point. So what is the change in enthalpy? H2 minus H1. So if I multiply the if you have to cancel out this negative sign, then that will be your H1 minus H2. So accordingly, if you have to consider the condenser, so see the condenser, here the 2 point is your inlet, state 2 is your inlet and state 3 is your outlet. So condenser is a heat rejection, so Q is W is equal to 0, then Q out is equal to H2 minus H3, because heat rejection is taken as negative. So heat rejection, heat addition, WP, W2 will be calculated. Then you have to calculate the efficiency is equal to W net by Q in. So if you put W net is equal to WT minus WP, what is your WT? H1 minus H2, WP is your VF3 into P1 minus P2. Then what is your W net also according to your first law of thermodynamics? For a cycle, Q in minus Q out. From this also you can calculate the Rankine cycle efficiency, that is your 1 minus Q out by Q1. Q out is your H2 minus H3, Q input is your H1 minus H3. Okay. Next we will discuss the effect of operating variable on Rankine cycle.